Welcome back to the deep dive. We are continuing our journey through the online encyclopedia of integer sequences, the OEIS. It's such a crucial tool, especially if you're working in number theory.
Absolutely invaluable.
Today, we're zeroing in on one sequence, A000222. It's got this link to a pretty neat combinatorial puzzle. It represents the coefficients of the Menage-Hit polynomials.
Right.
You might see it under old names, too, M2602 or N100229.
And the OEIS is just filled with gems like this one. A000222, it's a great case study, really, how a specific problem, combinatorial counting, generates this sequence that, it connects to deeper maths.
And that problem is the Menage problem, right? Arranging couples.
Exactly, the classic setup. Couples around a circular table, men and women alternating, and crucially, no husband and wife sitting next to each other. That's the starting point.
But this sequence, A000222, it goes a bit further than just the no one sits together case.
Precisely. These are coefficients of the Menage-Hit polynomials. So it's about counting the arrangements where exactly some number of couples do end up sitting together. It's not just the all-separated scenario.
Okay, so it gives a more detailed picture.
A much richer picture, yes.
So our goal for this deep dive, then, is to sort of unpack what this sequence is telling us. Why is it interesting? Why does it matter in combinatorics?
Good plan. Let's get into it.
Okay, let's look at the numbers themselves. The OEIS entry gives the terms. Starting from index 2, it goes 1, 3, 6, 38, 213, 14, 79.
Yeah.
They get big fast.
They really do. You see 11692, 1204, 364, then over 1 million, 10 million.
Mm-hmm.
Keeps climbing dramatically.
And there are those initial zeros at index 0 and 1.
Mm-hmm. Those make sense intuitively. If you have 0 couples, or just one couple, the whole alternating gender, no adjacent spouses thing around a circle doesn't really set up the conflict properly.
Right.
The problem really kicks in, and the counting gets interesting once you have at least 2 couples, hence the one at index 2.
And that rapid growth after that.
That's a huge clue. When you see numbers exploding like this in a sequence that comes from counting arrangements,
Factorials.
very often points towards factorials, yes. You're dealing with permutations, fundamentally, but with constraints.
Yeah.
The number of ways to arrange things just balloons.
The OEIS entry points us to Jerry Ordens, An Introduction to Combinatorial Analysis, page 198. That's quite an old reference, 1958.
Oh, Riordan's book is absolutely foundational in combinatorics, a true classic.
Yeah.
The fact that A000222 is in there shows it's not some new curiosity. It's been recognized as important for a long time.
So digging into Riordan would give the sort of original context.
Definitely. For understanding the early thinking on these polynomials, Riordan's where you'd start.
And, of course, Neil Sloan's name is all over this. It's in his 1973 Handbook of Integer Sequences.
Mm-hmm.
And then the big one, the Encyclopedia of Integer Sequences, with Simon Plouffe in 1995.
Sloan's contribution, cataloging these sequences, it fundamentally changed how mathematicians work with them. Having A000222 included in those major references really cemented its importance. It signaled, pay attention to this one.
Okay, let's talk about that growth again. Vaclav Kotasek provides an asymptotic formula. He says AN is approximately 2 divided by E squared times N factorial.
Yes, that's fascinating.
Yeah.
The N part confirms our intuition, the factorial growth from the permutations.
Right.
But that constant factor, 2 over E squared, that's more subtle. It comes from the specific rules of the Menage game.
The alternating genders, the no couples together rule.
Exactly. Those constraints mean not all N permutations are allowed. This factor, 2E2, which is about, 0.27,
right.
It tells you roughly what fraction of the potential arrangements do satisfy the rules, especially as N gets very large. It quantifies the inefficiency imposed by the rules.
That's neat. Then there's this divisibility property noted by Mark van Hoe. This looks interesting. For any prime p, an plus 2 times am plus p plus an plus 2p, that whole sum is divisible by p.
That is interesting. Properties like that, divisibility rules, especially ones that hold for all primes, often signal some deep underlying structure, maybe algebraic, maybe combinatorial.
What kind of structure?
Well, it suggests you might be able to group the actual Menage arrangements somehow, maybe in bundles whose sizes relate to p. It makes you wonder if there's a direct combinatorial proof, a way to physically partition the arrangements that explains why this sum is always a multiple of p. It's quite non-obvious.
The entry also gives Mathematica code, Jean-François Alcover, based on Vladeta Jovovich's work. It uses a summation with x and y.
Ah, right. That points towards generating functions. Very common in combinatorics.
How does that work here?
Likely the x and y in that formula are placeholders, Maybe X tracks the number of couples and YAR tracks the number of hits, the number of adjacent couples. The code calculates a polynomial or a series in X and Y and the coefficients of that series.
Are the terms of A000222?
Exactly, or closely related to them. It gives a computational way to find the terms, but also hints at this powerful generating function framework behind it.
Another connection mentioned is that A000222 is a diagonal of A05A057. What does being a diagonal mean in this context?
Think of A05A057 as the entries of a big two-dimensional table or array of numbers. If you read off the numbers along a specific diagonal line in that table,
You get A00000222.
that's the idea. It usually means the two sequences are closely related. Perhaps A000057 represents a more general problem, and A000222 is a specific slice or case of it. Looking at A058057 might give you a wider view of the mathematical landscape here.
And speaking of the landscape, the OEIS helpfully lists neighbors. A000219, 220, 221, then skips our 222 and goes to 223, 224, 225.
Exploring those neighbors is always a good tip. Sequences listed close together often share mathematical DNA. They might be variations on the Menage problem or related counting problems. It's like exploring a neighborhood. You learn more about the whole area.
We also have the keyword non-negative integers. Makes sense for counting.
A basic sanity check, yes. You can't have a negative number of ways to see people.
And approved by Sloan and Plouffe, the legends themselves, last modified May 13th, 2025. So it's actively maintained.
Shows the OEIS is a living database, always being updated.
Okay, so wrapping this up, this deep dive into A000222, it's really shown us a sequence that comes straight out of a classic puzzle, the Menage problem. But it's not just about the puzzle, it's about the coefficients of these hit polynomials.
Right, counting those specific arrangements with a certain number of adjacent couples.
We saw that near factorial growth, pinned down by the asymptotic formula.
With that interesting 2e2 factor,
That surprising divisibility rule involving primes.
which hints at deeper structures.
And connections to generating functions via the code and its place as a diagonal of another sequence. It's really embedded in this web of combinatorial ideas.
Absolutely. For anyone studying number theory or combinatorics, this sequence is a fantastic example. It starts with something quite tangible, seating people, but quickly leads you into asymptotics, number theory properties, generating functions. The OEIS entry itself is a launch pad for further study.
So here's something to chew on, a final thought. That divisibility property an plus 2an plus p plus an plus 2p divisible by PSE. Could that arithmetic property actually be seen in the arrangements? Is there some symmetry, some way to group the valid Menage seating plans, maybe based on rotating bihabiations or something? That naturally explains why that combination is always a multiple of T-Babel.
That's a really nice question. Connecting the arithmetic back directly to the combinatorics. That's often where the most elegant insights lie. A great avenue for further thought.
Definitely something to explore. Thanks for joining us on this deep dive.